Gravitational waves are big news in science at the moment because we now have the means to detect them directly. They're so weak that fantastically sensitive detectors are needed to pick them up. The first detection was made on September the 14th, 2015 by LIGO, the Laser Interferometer Gravitational Wave Observatory, which is operated jointly by Caltech and MIT. The source of this first confirmed detection lay 1.3 billion light-years away. It was two black holes, one with a mass 29 times that of the Sun and the other 36 times as massive as the Sun, that had been orbiting around each other and then collided. In the final fraction of a second before they merged, these black holes released more than 50 times the power of all the other stars in the observable universe combined. It took an event this titanic to cause a tremor in the LIGO detectors that could be measured, a wobble about 1/10,000th of the width of the nucleus of an atom. So what are gravitational waves? First of all, imagine that the space around us is like a stretched sheet of rubber. And when I say space, I really mean space-time, because in modern physics, space and time aren't separate. They're part of a four-dimensional thing called space-time. Where space-time is empty of all matter, it's flat, like the undisturbed surface of a trampoline. But anything with mass causes space-time to curve, just like if you stand on a trampoline, you make the rubber dip down. If you jump up and down, you cause a disturbance to travel across the surface of the trampoline. Exactly the same thing happens when a large, concentrated mass far away in the universe moves suddenly. It causes ripples to travel out along the surface of space-time. Eventually, these ripples, traveling at the speed of light, reach us here on Earth where, with sensitive enough instruments, we can detect them. Actually, any mass, however small, that changes its state of motion gives rise to gravitational waves. But gravity is incredibly weak. It's so weak that you can pick up paper clips with a magnet, proving that the little magnet exerts a force, electromagnetism, that's more powerful than the gravitational pull of the entire Earth. To put it in figures, gravity is 1 billion trillion trillion times weaker than electromagnetism. So to produce gravitational waves that we have any chance of measuring, you need large, fantastically compressed masses suddenly undergoing rapid accelerations. The sort of things that happen when black holes or other collapsed objects such as neutron stars collide. The existence of gravitational waves was first talked about by physicists such as the Englishman Oliver Heaviside and the Frenchman Henri Poincaré more than a century ago. They're predicted by the equations of Einstein's theory of general relativity, and we got indirect evidence of them in 1974 from measurements of a star system in which two pulsars, radiating neutron stars, are orbiting around each other. Astronomers found that the orbits of these pulsars were decaying, getting smaller, by exactly the amount predicted if they were steadily losing energy by radiating gravitational waves. Now we have not just indirect evidence, but direct proof of gravitational waves. Since that first detection in 2015, there have been others, not just by LIGO, but also by another gravitational wave observatory called Virgo in Italy. The exciting thing about gravitational wave astronomy is that it opens up an entirely new window on the universe. What's more, it promises to give us valuable information about some of the most extreme events that we know, including black holes and neutron stars in binary systems, supernovae, and the formation of the universe itself.